publish my data, then still the threshold is too high, so it's too complicated. So we have yet to come up with a simpler mechanism to enable people to essentially publish their data. But what we learned that the scientists are quite happy to use calibrated data from others, but when they find something really interesting, they need to get back to the raw data. But originally, the idea was that we develop the detailed data models and then build the services. We learned the hard way that developing really precise, high-level data models take a very long time. It was almost a decade before these things started to emerge. Had we waited through all those years in building the services, we still would not have even the core of the virtual observatory around today. So this has to be done with a healthy amount of compromise. Another lesson that we learned was that robust applications are hard to build. So typically, if we wanted to take something that worked and then make it just a little more robust so that it's really usable by outsiders of the narrow group that built it, it's already a factor of 3 more work. Another lesson was that we have geospatial everywhere, but we cannot just take off-the-shelf GIS software and run it. So basically, in astronomy, we need polygons where we have small circle boundaries. We have to be precise to a few milliards seconds, but the polygons can have an extent of 120 degrees on the sky. We have archives on all scales and all over the world. And one recent very nice idea is emerging, which is VO-space, so that it essentially enables users to hold their data at different locations all over the world, but still have a common view of it. So it's basically a distributed data repository service for individuals. So they can move their own data from one location to another to deal with this geographic diversity. So why is astronomy special? So this was a question that Bill Gates asked from Jim Gray on one of his annual evaluations. And so he asked that, okay, why are you spending half your time working with astronomers? And Jim told Bill Gates that because their data is worthless. And the worthless was meant in the most complimentary sense, that essentially there are no commercial interests tied to astronomical data. You don't need the lawyer to sign non-disclosure agreements. The data sharing agreements are usually very reasonable, so people are sharing their data after 6 months or a year of a proprietary period. So it has no commercial value. It's real and well documented, it has spatial and temporal features, and it's diverse and distributed. So we started to face the same problems that now Google and the other search engines are facing essentially 10 years earlier in a way. And the questions are interesting, and there are already today, there are probably petabytes of astronomy data around. So let's skip to simulation. So turbulence is the archetypical numerical hydro computational fluid dynamics simulation, and then the problem. And Feynman called it the last unsolved problem of classical physics. So there is still a large community working on it, because turbulence is so important for so many areas of our daily lives. So basically how the planes fly and how the internal combustion engines work. So for all of these, for the mixing of the fuel with the air, you need to understand turbulence. Yet, it is very difficult to run these high-resolution simulations because typically the analysis is done on the fly. So we run a simulation, and then we perform the analysis while the simulation is running, and then we throw it away. And as the simulations are getting bigger and bigger, it's only a smaller and smaller community that is able to run this simulation. And basically, it's becoming harder and harder to share this data among a broader community of users. So we came up with a new paradigm: take a simulation, store every time step of it in a database with a spatial index that was derived from the astronomy indices, and then give users the ability to insert test particles, little sensors into the simulation, which then report back the fluid velocity. Now, I would just like to run through, so there are now several papers coming out of this. This is the detail of the simulation with a Reynolds number of 430. And this is the view of the spatial index that we use. So the data is broken up into little blobs, which are then organized along the space-filling curve for a very fast spatial access. And then in the database, you can do things that you cannot do in a normal hydro simulation. You can run actually time backwards. And for example, put down a whole bunch of test particles which are on the circumference of this square, and then check where were they just a little bit before. And this figure shows a couple of papers that were generated using this public facility. So if you go to turbulence.pha.jhu.edu, then there are downloadable toolkits that enable you to play with the simulation from your laptop. This shows a typical daily usage of points. On a good day, we deliver about 100 million points to the user. Cosmological simulations are also growing in size. A few years ago, excuse me, I have a really bad cold. A few years ago, the cosmological simulation had about 1 billion particles and produced 30 terabytes of data, and the archetypical of these was the Millennium simulation. And then we build up dark matter halos and check the merger history of these halos, so we have to run friends of friends algorithms, which is basically graph traversals. And then we try to create a realistic universe. But still, using flat files, it was very, very hard to analyze the data afterwards. We needed a database. And so once the Millennium simulation was put in a database on a Slowlight interface, hundreds of people signed up and started using and analyzing the data. And the next generation of simulations will have over 1 trillion particles and output approaching a petabyte. So one of the examples is the Milky Way laboratory, a simulation that already obtained 15 million CPU hours from the DOE at Oak Ridge. And the expectation that it will generate about 500 terabytes of output. And here the test particles would actually be little dwarf galaxies that we can run afterwards once the simulation has been computed as a public facility. So we are designing this system now in collaboration with Pierre Romado, Ruzi White, and Connie Rakusi. And so this would be an interesting experiment how users can interact remotely with half a petabyte in real time. Let's jump sciences again. We have been spending quite a lot of time in exploring how to build the data systems for wireless sensor networks. So, and this scientific context is how can we monitor the environment, in particular the soil and its role in the carbon cycle. And we built a bunch of wireless nodes attached to the sensors themselves, which form a wireless sensor network. And so this shows basically we have hundreds of these out in the field around Baltimore, and some in Brazil and some in Ecuador, all over the world at this point. And these boxes work for about 2 years on a single battery and report the data in every minute to every 10 minutes, depending on how they are programmed. And this just shows essentially our data that we have accumulated just in terms of sensor days. So sensor days when one sensor was alive for a day, And a year ago, we were at around 180,000 sensor days. And this whole project was built on a $100,000 budget. So it's really a shoestring. You can imagine what will happen when this really explodes in the context of NEON, the National Environmental Observatory Network. But also you can think of not just environmental sensors, but even when you build a supercomputer with hundreds of thousands of processors, essentially many of these components are going to fail. So in order to monitor the behavior of the system, we have to have a sensor stream which analyzes every one of the components of the system. And of course, this is so much data that in order to essentially see and predict when a failure will happen, we have to run some very, very fast algorithms in real time on top of this sensor stream. So this is becoming, I think, a very, very important aspect of scientific computing. But also in radio astronomy, people are building now such radio telescopes where the data rate will be over a terabit per telescope. And essentially, there's no chance that we can even capture this data. The data will have to be analyzed on the fly. So data-intensive computing doesn't necessarily mean just accessing data from the disk. This shows that we have to be able to access data from real-time streams as well. So what are the commonalities? We have huge amounts of data, we need aggregates, but we also need to keep the raw data. Because of the sheer size of the data, we have a large need for parallelism. But we found that the usage patterns enormously benefit if we can use indexing. So the geospatial, we have to very often extract small subsets of large data sets, we have to compute aggregates. So in everywhere that we have been doing, we found that fast sequential performance is critical. So in a way, if the data could not be accessed in a sequential fashion, then the analysis could not be done or cannot be done. So most of the data organization starts that we have to lay out the data in such a way that most of the analysis can be done in a sequential pattern. The pitfall is that the data will never be in one place, and this is a fact that we will have to live with. We just have to kind of come up with good heuristic algorithms, how can we minimize the data movement. And overall what we found is that these patterns fit a database quite well, but we don't need all the features that the traditional databases offer. It's okay to have a database without transactions. And how can we take in this way the analysis to the data? So the methodology that we have been working on this, Jim, over all these years is to take essentially class libraries that have the scientific smarts and then link them with the database. So run all these class libraries inside the database. So this is the ultimate way of taking the analysis to the data. So how long does this data growth continue? The high end is always linear, so think of CERN. So once the LHC was turned on, it will be another 15 years before there will be a new detector or a new accelerator built. So until then, its data will come at a constant rate, so basically the data size will grow linearly as a function of time. So the exponential comes, what we can see with the sensors or with the CCD, that every 2 years we can essentially throw away the old detectors and then replace them with new ones at the same for the same price. And so just like we do with our computers. So the question is that how many new generation of instruments do we have left in our respective areas of science? And it would, in some cases, it would be, the outlook would be grim, unless we realize that also software is becoming a new kind of instrument in its own right. So first of all, we take some huge data sets and build a federated version of them. So we take several large data sets and merge them into one. Then once we perform this computation, it's worthwhile saving it. We can, more and more fields, even biology, building huge numerical simulations. And then we also see this multi-tiered hierarchical data replication like in high energy physics.